Hello, everyone. Welcome to this afternoon paper session of EuroVA 21 called the Temporal Data and Clustering. I'm Cagatay Turkay from University of Warwick. I'll be the chair for this session. So hope you all enjoyed your lunches. I wish we were having the lunch together, but it's not possible. But really excited to start this afternoon session with a great lineup of papers that look at different aspects of temporal data and ways of involving clustering within visualization and visual analytics. And on top of that, we have a special session, not only because we have all great papers, but also we have an honorable mention and a best paper lined up. So we'll start with the first talk, which is an honorable mention award for this year, EuroVA 2021. It's towards the detection and visual analysis of COVID-19 infection clusters by Dario Antweiler, David Sessler, Sebastian Ginzel, and Jörn Kohlhammer. And I'll just want to sort of congratulate all the authors and look forward to the discussions after we listen to the talk.
Hello everyone, my name is Dario Antweiler. I'm with Fraunhofer IIS Research Institute in St. Augustin, Germany. Together with my colleagues David Sessler, Sebastian Ginzel, and Jan Kohlhammer, I studied visual analytics for COVID-19 contact tracing networks, and today we would like to give you a short presentation. Our workshop paper is called Towards the Detection and Visual Analysis of COVID-19 Infection Clusters. The COVID-19 pandemic is highly dynamic in space and time, and local health authorities face the challenge of tracing and breaking the chains of infections. Their tasks include to obtain and learn from data, search for contact information, and analyze infection clusters. This is typically done manually and is a time-consuming process for both general staff as well as doctors. Our goal in this research project was to support the rapid identification and subsequent interruption of infection chains. In 2020, we started a collaboration with local health authorities in Germany to support them with visualization and analytics technology. The public healthcare system in Germany is organized into hundreds of local departments and the Federal Robert Koch Institute. Together with public health experts from multiple regional departments as well as the RKI, we identified research questions regarding the contact tracing data. We discussed requirements and interim results for a visual analytics system that can support the public health experts in their work. As part of our collaboration, we studied the COVID-19 dataset for Cologne, Germany, that covers a population of more than 1 million. The project included multiple feedback rounds to sharpen the research questions, as well as guiding our analytics framework. Public health officers build large contact and infection networks, spanning multiple generations of transmissions. In these networks, every node represents a person, and a directed link between two nodes represents a supposed infection based on conducted telephone interviews. By tracing back the source of an infection, individual clusters can be inspected and potentially contained. Unfortunately, in practice, only around 27% of SARS-CoV-2 cases in our dataset can be traced back to their source. This leaves the majority of cases disconnected. Therefore, one main challenge for public health officers is to efficiently identify missing connections between infected persons. We set our goal to build a visual analytics system that can achieve both the visualization of compiled infection routes as well as an analytics component using a machine learning model to predict missing links in the data.
Which brings us to the visual analytics system that we created as part of this project, with the goal to help PHOs or public health officers to identify, assess and visualize clusters in the COVID-19 contact tracing networks, and to include missing links to help find infection clusters, potential infection clusters. One problem with the data at the public health departments is they only contain one quite simple entries per contact and the contact networks, but not much more information. Many DPHs store more information, but this is the common denominator across different DPHs. There are also not many visualizations used on top of these databases in the public health departments. There are certainly many visualizations created during the last 12 months, and we refer to this COVID-19 related work. We refer to our related work section. One design decision was no data leaves the public health department. That is why we created the system in a way that the PHO can upload the data locally and visualize everything locally. Let's look at the main components of our system. It's a JavaScript web front end with using the framework React.js and Material UI. And you can filter, the PHO can filter down to certain patient IDs, set a minimum network size, or filter down to only symptomatic patients. There's also a filter for the time period. On the left side we have the epigant with the focus patient on top and all the contacts positioned according to the contact time below that contact. And we have the contact network, a directed graph using a force-directed layout. On the bottom left, you also have a legend with the different colors and symbols we use. Looking further into the epigant, we use an extended bar chart for each of the contacts. So there is a blue dot for the actual contact to an infectious person. Then we have the first symptoms in most of the entries. We calculate according to the model that the DPHs use. We calculate the infectious period. There's a test result positive in many contacts, and then the quarantine starts in most cases, and we extended that quarantine bar a little bit to make clear that this person is now in quarantine. And as I said, all the contacts of that particular content can be found below. There's additional information that you can access via mouse over. The contact network is a directed graph. There are many graphs in there, many small networks. That's why you should set a minimum network size, especially when you look for clusters, since most of the networks have 2 or 3 contacts. You can set the desired time period, and especially interesting are the predicted links. They are visualized as gray lines, directed, and they are dashed or widely dashed if they are near 50% and go up to 100% when they become solid gray lines. We want to give you a short demo to show our system in action. This example now is linked to the use case in our paper, where we particularly looked at care homes that were quite vulnerable last year during the COVID-19 pandemic. And our PHO looks into the different potential clusters in the region that she is responsible for, and has already selected a time period from August 6th to the 26th of August, as you see at the start and end of our time filter. She has also selected a certain patient ID 27065, and you can see that this with animation and the solid lines, that there's a larger contact network around him or her. You can also see that in the epigant, with he or she had first symptoms on August 12th, was tested positive a number of days later and then put into quarantine. And there are also a number of contacts. Some of them were tested negative, some were also infected and put into quarantine. What our PHO is now quite interested in are the predicted links that we can see. So solid lines are data in the DPH database. The dashed lines are predicted links by the algorithm of our system. And you see there's one directed link into the care home towards our contact, and our PHO wants to now look at this particular patient or contact. And we see a quite different epigant with a person here in the center that on the top that was supposed to be in quarantine since the 27th of July and was tested positive on August 12th. Since this link is predicted to be quite likely to this person, the PHO decides to look further into that in the documentation around those two contacts. In addition, she might discover some weaknesses in the containment strategy and, of course, can plan for different countermeasures to prevent further infections coming into a care home from the outside. She can also look for other time periods now, which would then change the network, or look at different patient IDs in this larger network, and especially look for larger networks or potential clusters in the region she is responsible for.
To identify missing infections between contacts, we analyzed our dataset containing more than 40,000 persons together with transmission routes. Our approach builds upon the link prediction task, where given two nodes in a network, the model decides whether a missing connection is probable. These identified links can then be visualized inside our system to support the analysis by the public health officers. For the classification task, we tried multiple different features, and after discussion with public health experts, we settled on a selection including the number of days between infection reports, the difference in years of age, and a binary feature encoding if the two people live in the same housing block. By using the housing block instead of an exact place of residence, our model can be applied to an anonymized dataset. Although typically more data is registered in practice, we select only a small number of features to retain high interpretability of results. Given over 11,000 index cases in our dataset that were positively tested for COVID-19, about 7,800 of them contain a suspected infection source. We selected all of those source target pairs and sampled 40,000 additional pairs who aren't connected to include negative examples. After a train test split, we trained our model on the training data to classify an edge as either high or low probability of being a transmission route. We compared multiple classification model architectures, including decision trees, random forests, naive Bayes classifiers, and support vector classification. Hyperparameters were selected by performing a grid search and cross-validation. Comparing them on the test set via area under the receiver operating characteristic, the random forest model achieves the best performance, although all other models are close. We select the best performing decision tree model for our visual analytics system as it contains the highest interpretability of all models. This is one of the most important qualities of an analytics system used in healthcare. Our model can easily be scaled up to a large number of nodes and generates classification results in a matter of milliseconds. We regularly discussed our framework with healthcare professionals to gather and integrate feedback. During these sessions, the combined timeline and network-based view was perceived helpful for the comprehension of the spatio-temporal dynamic. Selecting specific timeframes was important for the users to focus on a single infection cluster and understand their behavior. The display of possible missing transmission routes was viewed as supportive for the detection of infection clusters. This is especially important with new mutations of SARS-CoV-2 arising, such as happening right now worldwide. To conclude, our visual analytics system shows infection clusters and identifies possible missing connections with a machine learning component. We received positive feedback from multiple public health officers. Although our framework can be applied to any infectious disease, there are still some limitations. Based on the available data, the analysis is confined to single regions, while infections spread across all political boundaries. To address this, we would need harmonized datasets across all public health departments. This would also benefit the prediction results of our machine learning component. We are looking forward to extensions, such as the integration of public health measure data, like restrictions and curfews, to visualize and analyze their effects on the pandemic spread. Additionally, up until now, we don't integrate any epidemiological parameters into our missing link prediction. Comparing the data with scientific research on serial intervals and reproduction factors might enable even further analysis. I would like to thank my collaborators and acknowledge the support of the Fraunhofer Cluster of Excellence, as well as the Competence Center for Machine Learning Rhein-Ruhr. And of course, thank you for listening. We are now available for questions, and I also would like to pose the following questions to the audience. Which other application areas are suitable for combined timeline and network-based visualization? And how can we effectively incorporate a visualization of public health measures into our framework? Thank you very much.
First of all, thank you very much, Dario and colleagues, for the really great work and really great presentation. And again, congratulations for the honorable mention once again, this time in person.
Thank you so much.
Yeah, great. So I'm sort of monitoring the chat, the Discord chat on the side, and I'll encourage everyone to ask your questions and comments to Dario. Like I'll while those questions are piled up over there, I'll just want to start with one question about the sort of very particular context in this application, the pandemic, and we all experience that. Those of us who are working in that domain, there has been a great time pressure, right? I mean, like within this context, some response needed to be given quite quickly. Public health experts, they were under intense pressure, resource-wise, intense pressure under of the situation, and they needed to respond very quickly to lots of unknowns. So how did you get around working with the public health experts? How do you manage to just get a bit of their time in your collaboration?
Yeah, thanks. That's a really good question. So for us, it was really important to start early. So this was part of a bigger initiative from Fraunhofer to support public health authorities in any way possible. It could be data analysis, it could be visualization, any help was being offered. And what another great part was to ask the people what really was their first need. So we thought about fancy visualizations and analysis, but most of the time, really simple answer to some of their questions was much more important. And in that way, we said, okay, we are doing only 1 or 2 hours per week. We talk about our new ideas, about their new ideas, and we get really a direct feedback to the ideas we had. And so anytime there was a really big wave going around and they didn't have much time for us, we actually slowed down our progress and really focused on some improvement on already existing concepts. But it was really helpful for us to get really big feedback and detailed feedback and integrate that into our framework.
That's really great. Thanks, Dario. There's one question from Jan. Jan adds on the data side, and then he's asking about the raw data. I mean, because it differs from country to country, was this based on some logs kept by hospitals? I think you mentioned phone calls. Can you tell us a bit more?
Sure, I can elaborate on that a little bit. So actually, it's really just like we told you in the paper. It's really dependent on the local context of the health authorities. There are many hundreds in Germany which are doing it before the pandemic, at least very differently. And in Cologne, we had really the luck that there was already a sort of systemic approach in place. So every time someone was being reported as a positively detected COVID patient, they get a call as soon as possible from the public health department, and a structured or semi-structured telephone interview is conducted. And this data was being put into a database, into a system, and they kind of impose rules on themselves on what the data that goes into there should look like. And they actually provided us with a really quality data set where we deleted some of the data to protect the privacy. So this was one main component of our approach, that we wanted to analyze the data and to identify some missing links, even if we only have anonymized data available.
That's great. And about the location, I mean, one thing I was sort of curious about was the location. I think there's also a bit of that in Jan's question. Did you have like GPS coordinates or sometimes, or just like buildings or anything about location?
Yeah, so we had some geographical data available. This was a semi-accurate location of the place of residence of all of the infected people. So we talked with our data protection and privacy officers and the ones from the public health department, and so they set up a sort of in-between possibility to get I think it's one block of houses. You can imagine it by that. So we knew if somebody was in block A or in block B, but not more detailed.
Yeah, I mean, there's also a comment from Jason about the privacy concerns and anonymity of the data, and that was one of my questions as well, but you responded to that already.
Yeah, maybe
privacy is a big issue in these kinds of visualizations, right?
It is, and it was for us, and we wanted to make sure to develop something which could be used in Cologne, the partner we had, but it could also be used somewhere else, and also be working with data where no any personal information is being a part of it. And so this housing block was really something we discussed a lot about, because in a city like Cologne with more than 1 million inhabitants, a housing block really contains many hundreds of people all the time. But actually in some other places, it might be the case that there are far fewer people being part of a housing block. And when you have age group and something like that, it's really hard to protect privacy. So this should also be a more detailed research question on whether this could be transferred onto other regions with other structured population.
Yeah, great. Thanks, Dario. I mean, just very, very final maybe comment or maybe a question related to what Jason posted on the chat about being ready for the pandemic as a community. From your personal perspective, developing this solution, how did you find the visualization literature sort of helping you, guiding you in the design? I mean, was it sort of in a way straightforward to think of suitable designs and responses to visualization based on what we have been doing in the community?
So to be honest, I'm quite new, a member of the visual analytics community. So maybe we could get the opinion of some other people who are more experienced. But we did a lot of related work, research to look for solutions available, and we found multiple ideas on how to visualize that and tools available, but we didn't really find much of the tools being used actually by public health departments up until now. So we had some literature found for Ebola cases in Africa, for example, and some few examples for infections inside of hospitals, tracing and tracking those. But it was actually interesting that a lot of these tools and methods weren't really being used by people in public health expert fields. And so at least for Germany, we could tell that there was a lot of room to actually get the developed methods from the community into the hands of people actually using them.
That's great. And thanks for doing that translation. Thanks for doing that work. Thank you very much, Dario, once again, and congratulations once again. And that was a very nice discussion as well.
Thank you for being part of this.
Thank you. Hello, everyone. Welcome back again. So the next talk is again one that's inspired by the challenges that's brought up by the pandemic that's been going through. I think it's another good sign that we are responding as a community and building that body of literature with techniques and methods. The next paper is called LFPeers, Temporal Similarity Search in COVID-19 Data. It's by Jan Burmeister, Jürgen Bernhard, and Jörn Kohlhammer. And for those of you who were not in the opening session, this is the best paper for EuroVA 2021. So congratulations to Jan. And we'll see that it's also be a technique and method paper that's just providing some solution for the challenges brought by the COVID-19 data, but also more generally. So after the talk, we'll have some time for discussions. So off to Jan's talk.
Welcome to our presentation of LFPeers, Temporal Similarity Search in COVID-19 Data. This is a work by Jan Burmeister, Jürgen Bernhard, and Jörn Kohlhammer. I will begin by a brief motivation, what made us working on this project, introduce the generalized concept of our approach, and finally present our implementation, LFPeers. Looking back at the year 2020, hardly anything had such an enormous effect on our personal life, business, and politics than the COVID-19 pandemic. Going back to the spring of that year, there were two factors that made us start working on this project. First, the world observed the first wave of COVID-19, notably, however, quite differently depending on the country. While some countries were hit hard and put into effect respective countermeasures, others did experience a much less severe situation. Discussions about these model countries, what they have done differently, and what one can learn from them, became a popular topic in the media and internet discussion boards. Second, we saw a rise of COVID-19 data visualization dashboards from all over the world. We all know the famous board from Johns Hopkins University, the New York Times, or here in Germany, the RKI dashboard. However, there were many, many more, created by official institutions, news media, or just data science enthusiasts and students. One of my colleagues actually kept a list of more than 150 dashboards he found in just the first months of the pandemic. Looking through this list, we observed that most of them serve the purpose of merely data presentation. They show how situations are like, how measures have developed over time. However, less approaches also help explain why situations have emerged or why trends developed the way they have. Learning from such underlying mechanisms is of course crucial for understanding such complex situations and to make informed decisions in the future. Those were the core questions that started this project. Why are countries sharing a similar situation starting to deviate from each other? Can we find causes for these divergent behaviors in static or temporal conditions? and can be learned from peers, in this case similar countries, to make informed decisions. Based on a public dataset aggregated and curated by Google, we started working on our concept to see if we can solve this question with visual analytics. The dataset contains both recordings of observations, for example regarding epidemiology and mobility, as well as recordings of potential influencing factors, such as government responses and weather measurements. This is our approach. These questions led us to a rather special two-phase analysis problem. Consider the graphic on the screen. The lines depict an observed attribute over time. One curve, one country. The highlighted group in orange shows very similar behavior until a certain point. After that, these countries suddenly display a variety of different progressions. We want to find out what might have caused this behavior. The analysis starts with a search phase, where an analyst identifies a set of most similar peers based on user-defined similarity. The result of this first phase is a set of peers that the analyst considers similar until a chosen time point t0. The choice of the time point t0 is left to the analyst. For example, the analyst might select an exact date where some policies and measures were introduced to study their effect. Alternatively, the analyst may choose a time point where observations displayed notable changes, for example a sudden rise in infection numbers. The search phase is followed by an exploration phase, where the analyst performs a detailed analysis of the similarities of temporal progressions after the chosen time point and tries to find correlation that might explain these observations. We want to emphasize that we believe this project is generalizable to many application areas, basically to every area where a set of synchronized time series are observed for a collection of data objects. Consider, for example, a collection of industrial machines, each observed by a set of sensors, or consider a medical study, where the participant's reaction to a stimulus is measured. In each case, we might observe interesting behavior in a subgroup of the data entities, and we want to discover what factors, static or temporal, might have influenced these countries, machines, or participants. These are the tasks along the user workflow that we have identified. First, there's the search phase to retrieve the most similar objects prior to T0. First task is to select and analyze an object of interest, in this case a country. Second task, define T0 after the analysis of the object of interest. And T3, identify peers with most similar behavior before T0. Then we continue with the exploration phase, where we explore variances within peers after time point T0. We first explore commonalities and differences of peers after this time point, and then correlate post-progression of peers with external factors that may explain variations of peers after T0. So finally, we present LFPeers, short for looking for peers. This visual analytics system implements this conceptual workflow in two dedicated phases, one for the search phase, one for the exploration phase. Let me walk you through the interface in the order a user would use it, which is the same as in the order of the workflow task that we just set up. First, we're starting out with selecting a country of interest. The straightforward way is to directly select a country from an autocomplete combo box in the panel in the top left corner of the interface. This panel provides all available data of the selected country, structured in different tabs by category. The selected country, in this case the United States, is highlighted with a green-blue gradient line. We will come back to our color scheme in just a minute. On the right is a world map that can be colored in different ways. The user can select an attribute and project its values onto the globe to explore for notable and outstanding countries. The globe can display the values for a single point in time, or the difference between two time points to display the development of an attribute. If the user finds a somehow outstanding country in this view, he can select it for the analysis by simply clicking on it. Alright, now we want to find peers, similar other countries to our selected country. For this, we need to define a time point T0 of interest and define how we want to determine if another country is similar. To do that, let me first describe how our concept of defining similarity works. Similarity is always determined based on the user's selected attribute. Remember the charts in the detailed section? The user can simply brush on any attribute chart, thereby defining a query attribute and range, in other words, the time point T0. In the images on the left, the user has selected a time point T0 somewhere at the first quarter of the two time series. The selected time range is marked with a gray background. Once the user has performed a brush action, the system will sort all countries by similarity based on the selected query range and attribute. For each country, the query range of this attribute will be mapped onto a feature vector. These vectors are then sorted by the distance to the feature vector of the query country. Our system provides several operators for the mapping and sorting. In the default case, the data will simply be sampled equidistantly onto a target number of samples and then sorted by the Euclidean distance. You can see an example for that in the image on the left. The Euclidean distance compares the values at every time step independently. So if you want to look for countries where the development of an attribute is very similar in value and in time, you would pick this combination. If you care about the shape of the curve, but it is not that important for development to happen at exactly the same times, dynamic time warping is the way to go. The image in the middle displays a set of similar time series in shape, but with different offsets in time. As an alternative to downsampling the query range, the system can also map onto a single statistical value, like the minimum, maximum, or trend within this range. For ordinal attributes, for example an attribute that measures the strength of a certain government restriction, you might only be interested if a country has reached a similar value, but you do not care when this event occurred or in what circumstances. For trends, you might only be interested how a value has increased in this time range, but not so much if the increase came abruptly or slowly. The exact setting is certainly depending on the analysis question the user wants to answer and the way the user wants to define similarity. This is how the result looks in the interface. The table presents the results of a sort operation. Each table row contains a checkbox to decide if the country shall be included into the group of peers. A bar that displays the similarity of this country and a set of static and temporal attributes that the user can freely define. Static attributes are displayed by colored cubes, temporal by gradient colored sparklines. The table is sortable by selection, similarity, and static attributes. By browsing through this outer table, the user can select until which point he considers countries similar enough to include in the peer group. You might have wondered about the gradient. We noticed that a densely stacked display of sparklines becomes quite hard to read, because there is no real reference about the y-axis range of each chart. Especially with a collection of very different time series, it kind of just turns into a bunch of stacked lines that one cannot really compare to each other. Because of that, we apply an additional gradient that mirrors the y-axis. Blue for low values, green for high values. Consider the first chart on the upper left, and the same version with the gradient applied on its right. The high values and spikes in green directly hit the eye, making it easier to compare these series with each other, at least on larger scale. The second row displays the curve of an ordinal attribute. The gradient emphasizes the plateau at the start that all series have in common. After that, the coloring highlights that especially the upper time series go back to a relatively low value, coded in blue, whereas the bottom three remain at a higher level, coded in green. When browsing through a large ordered table, this coloring helps to quickly spot such differences. For consistency, we use this color scheme for all other charts as well. The gradient always depicts the currently described entity, orange the set of selected peers, and gray the remaining countries in the background to provide a global context. The table is accompanied by two auxiliary views to help the user make their decisions on peers. The world map can also be set to display the set of selected peers on the globe. This is useful if you want to get a quick overview of which countries you have actually included. You can also select and deselect countries here, for example if you want to focus on specific areas of the world or if you are missing a specific country. At the bottom right, we have placed a scatter plot that displays a t-SNE projection of the feature values. This is useful to see if the countries are grouped into clusters. The selected country is highlighted with a crosshair. If you notice that the query country is located within a cluster, selecting the cluster peers to start with seems like a good idea. These three views each provide a look into the data from a different perspective and are linked together to help define the group of peers. So far, we have defined a peer group using only one attribute. Our system actually supports up to 4 such criteria, each with its own similarity concept, sorted results, projection, and selection of peers. The final result is defined by the intersection of all these user-defined groups. In other words, the countries that satisfy the similarity selection of all criteria. This is the set of peers that will finally be used in the exploration phase. Here's the section of the interface. You can see currently 3 slots, each depicting the query attribute and the included countries drawn in orange. Right now, the second criteria is selected, meaning the interface displays the state of this criteria. So this is the search phase interface. In this example, the user has defined a peer group using 3 criteria for similarity, which will now be used in the exploration phase. Note that we can always switch between the search and exploration interface. So if we notice our peer group is, for example, too small, we can always go back. Alright, so now we want to explore what happens after the time point t0. How is our peer group evolving, and if there are differences, can we find factors to explain them? We are starting pretty straightforward by presenting all the attributes on one large grid for visual inspection. This is the point where the user can spot interesting behavior, such as the time series fanning out or diverging to 2 defined groups. In addition to classic line charts with the color scheme you already know, we use a combination of heat map and line charts for ordinate attributes. The time domain is discretized here to aggregate the values of the context countries as heat maps in gray. The peer group in orange is displayed as randomly jittered lines. For example, on the right chart, we can see that the peer group mostly follows the behavior of the rest of the world, being especially similar to start. Similar but more diverse behavior can be witnessed in the other charts. If one has found some interesting behavior, for example here a notable fanout, we want to see if we can find other data to explain this behavior. By clicking, the user can select time points, marked here with blue line markers. The system then computes correlations between the values of this attribute at this time with all other temporal and static attributes using either Pearson or Spearman's correlations. The result, a ranked list of similar attributes, is displayed on the right. Upon demand, we can go into further detail and compare the correlation between 2 attributes at different points in time, visualized as circles below the chart. In this case, the attribute has shown high correlation for the whole time, so it is unlikely that this is the cause for the behavior in question. It is more likely that both attributes have been affected by the same cause. So this is LFPeers, a visual analytics approach for cause-effect analysis in temporal data, combining nearest neighbor retrieval and correlation analysis. We have demonstrated our approach using a COVID-19 use case, but we see strong potential for a generalization of this approach. We currently aim to extend the toolkit to open up the concept for other use cases, which require, for example, time series preprocessing or further special means to determine similarity. This has been my presentation. Thank you very much for your interest in our work.
Thank you very much, Jan, for the really nice presentation. And once again, congratulations to you and Jürgen and Jörn for your best paper award this year.
Thanks very much. Thank you.
I'll sort of encourage everyone to send your questions over Discourse, over the YouTube chat, wherever you feel comfortable. Well, I'm monitoring that. Actually, there is one question from Dario. Let's start with that. Dario's asking whether you consider analyzing bordering countries are often sharing similar behavior. I mean, in a way that whether there is some criteria in geospatial proximity. And then he also suggests that the border-based graph of neighboring countries could be an interesting integration to your analysis.
Yeah, so mainly what we're doing is comparing them without directly geographic reference. When you look at the table, we do have, of course, the world map, but there is no attribute directly linking neighbors together. That would be interesting. So you could say, let's say Europe is relatively close together, everyone. That you say you're only focusing using the map on specific countries in a specific area. That might be more difficult maybe in Asia or South America. But yeah, there is no specific attribute that's linking the different countries together in this sense. But yeah, combining this with this network would actually be an interesting idea. I think then we can have attributes that are actually linking countries. That would be really interesting. Yeah.
Yeah, and Jason makes a similar comment on Discourse that there is, I mean, one would expect some continuous geographic nature of the differences or sometimes where you expect similarities, you might be seeing differences, and then that might be relation to some sort of particular like characteristics of an area, right?
Something that you actually notice is when you're looking at policies, etc., that there are sometimes differences. Just in Europe, one country is doing it this way, another country is doing this way. There were differences that we actually did not expect. So yeah.
And in your interactions with the with potential users of these, have you come across this kind of requirement, this kind of need, looking at this geographically as well as temporally?
Not exactly, because this wasn't the primary question that we started this with. So the goal generally is to generalize this whole approach. Of course, the COVID-19 was the only starting point, because there was, well, yeah, the current situation, obviously. But we are certainly looking to extend it to other use cases as well. And then we are, of course, looking to user and do really evaluation of everything. So, yeah. But in this particular case, that wasn't the case.
Yeah, thanks, Jan. While others are thinking of some of the questions, I want to ask a bit about your decision to have this two-phase approach as a sort of like as an underpinning concept that you have in your solution. So you have the search phase and then the exploration phase. So can you open up a little bit why you went to such a sort of a, let's say, a structured approach to your analysis?
Well, we started out, there was this initial question. Well, the underlying question is you want to find out why peers that are very similar currently behave differently at some point. So it's just logically to split this in these two parts, find similar first, and then it's until some point, and then analyze how these develop. So this was kind of the logical way to do this from the requirements. So this was our initial question. Yeah, this was how it kind of logically followed from the requirements.
I think one sort of particular strength in separating these, I thought, was that rather than having a complex visualization that tries to do everything, all the tasks, I think one thing that this separation creates is almost a phasing of the tasks. So you first go through this search phase, come up with those peers, and then sort of dive into exploration. In a way, it creates these stages in analysis, which in some ways, I guess, you're guiding a particular way of doing an analysis, which I thought is good from both a usability perspective, but also maybe from a guidance, analytical guidance perspective. Great. Dario makes another point on geographic comparison. And then sort of raises this point. I think you can take this also maybe as a comment and some sort of idea for future work as well, that as there are subdivisions available for countries, so we could also look at whether countries some are more heterogeneous than others in comparison to others. I think that also maybe has an analysis potential at a single policy, but different responses in the same geographical setting, right? And then a question from Felipe. Did you consider comparing cities from bigger countries with other small countries?
No, because this was mostly based on the data set that we had. So there is some kind of detailed data available in this data set, but there were a lot of missing data because this is something that's not easily to aggregate, I guess. So we have been mostly focusing on countries itself. But I guess the question is, you do obviously have outliers with very small countries like Luxembourg or something like this that have a very different kind of demographic, etc., than a large country with various country sides and everything. No, we didn't have specific country data, but in generally, the idea is that the system is adaptable, so we can, if we get data from cities, then obviously we can add them.
I mean, looks like the questions are already quite a strong indication that there will be some interest in seeing a geographical spatial analysis layered on top of this temporal analysis, especially for cases like this. And you mentioned a bit about future work, and then this being applicable to different contexts. So can you open that up a little bit, and what with future directions that you consider, and how do you see this generalized to other problem contexts?
Yeah, so I'm generally more working in the medical field. What we had in winter, I guess, that kind of affected the development was we had a student doing evaluating studies from like patient studies where they also measured different vital data, and then they had some kind of some response. It was some kind of action, and then they measured from this point on how patients responded to that. And this is kind of similar. So we have time series that are somehow synchronized to this specific start point. And you want to measure, see if there are any subgroups, or are they, how are they compared to each other? And this is basically, if you switch countries to patients, then obviously you have a very similar idea. There are, which is like the world map, for example, that are certainly specific to COVID now. But you can also think about other things like, I think I mentioned the industrial case. You have machines that are observed by sensors. And if one machine at some point is doing weird things, then you might look at what point did that start, and then see, okay, can you find out what caused this? And I think there are quite a lot of use cases that we are certainly looking for. And additions, obviously there need to be a lot of additions regarding time series preprocessing. So we do have some operators like normalization and log transform and all of this. There's a lot more to make it really applicable to general time series data, like seasonality and periodicity, handling all of this. Yeah. So these are the big points.
That's great. And then there are sort of some further comments on bringing in like potentially some metadata related to the time series, like Gabriela suggests, looking at some like income indicators, and like Jason suggests, maybe even some confidence in the data, etc. But I mean, maybe you can continue later on these discussions on the Discord chat. But once again, thank you very much, Jan, and congratulations again for the best paper.
Thank you very much.
Thank you. Hello, everyone, again. So from that point that Jan left about maybe looking potentially into some of the features that time series might have, should we have a paper now that is trying to realize that, and using some derived data and some novel technique to look at multiple time series in a different space, in a different projection space. So the next talk is multi-resolution analysis for vector plots of time series data. It's by Dien, Nguyen, Tommy Deng, and Rattikorn Hewett. And Bao is going to present the talk now, and we will have some time for further discussion and further questions after the talk. Floor is yours, Bao.
My name is Bao from Texas State University. I will present the paper Multi-Resolution Analysis for Vector Plots of Time Series Data. The content has four main parts, including problem, visualization design, use cases, discussion, and conclusion. Let's move to the problem of this presentation. Let's firstly consider the structure of the data that we study. It has three dimensions, including data instant, variable, and time. In this presentation, I usually call data instant the data point. For example, we can get the death and birth rate of countries on Earth to illustrate this type of data. In this case, 201 countries are the data instance. Death rate and birth rate are two variables. Every timestamp is a year from 1960 to 2017. If we ignore temporal information and focus on each timestamp, we can use scatter plots to display pairwise relations between two variables. For example, the left scatter plot depicts the distribution of data points in 1988, while the right scatter plot shows the distribution in 1993. If we want to involve temporal information, we can use vector plots to combine any two scatter plots and depict the evolution of distribution over two timestamps. To clarify the advantage of vector plots, we consider an example data of health readings of computer nodes in a high-performance computing center. This data has 467 computer nodes in data points, two CPU temperatures and two variables, and the data is collected every 5 minutes. Because too many data points can lead to the cluster issue, we cluster vectors due to their coordinates and keep only one vector per row, and remove the other to get the vector plot here. As can be seen from the plot, vectors tend to point to a certain region near the middle of the plot. It implies that vector plots can directly display evolution of data point distribution, or in other words, we can gain both spatial and temporal information from this type of plot. However, vector plot cannot depict the whole temporal range. For example, this plot only illustrates the trend from 1530 to 16 o'clock. We don't have any information at any other timestamp, such as 1545 or 1605. We call the difference between two timestamps a resolution because it provides a particular level of details of the evolution. For example, from 1525 to 1555, we make a 6-step jump because the data is collected every 5 minutes. Similarly, from 1530 to 16 o'clock, the jump is also 6 steps. We can say that these two plots have the same resolution. However, the third plot depicts the next jump from 1555 to 16 o'clock with only 1-step jump. So this plot has a different resolution in comparison to the other two. It's interesting to answer the question, which resolution should we investigate? This presentation shows a visualization that can guide users to a resolution for interesting information. The next part is visualization design. If we select a pair of variables, all vector plots of each resolution form a sequence spanning a whole temporal range. For example, let's consider the death range and birth rate in resolution 3. We have a sequence of vector plots that fill the time range of the data from 1960 to 2017. If we look at the first time points of each plot, they increase by 1 step as we move from left to right, such as 1970, 1971, 1972, and so on. In most cases, it's impossible to analyze all vector plots in the sequence. It is the reason why we compute a selected visual matrix for each plot and use their scores for analysis. We have time series of the selected visual matrix, and this series represents the corresponding sequence of vector plots. In this presentation, we use two visual matrices from another paper, namely translation and entropy. Translation scores the amplitude of collective evolution in the units of size of the data point at T1. A high translation score indicates that most vectors have similar direction and their planes are significant in comparison to the size of the green dot circle. In contrast, a low scores mean that there is no similar direction between vectors, or their planes are small compared to the size of the green dot circle. For entropy, it's either permutation entropy. It's called the complexity and association and direction of vector in the plot. A high score implies Its vector may have a distinct direction, while the low scroll indicates the association in the direction between the vectors. Although we use these two visual metrics in the paper, our report methods work well for any other visual metric beyond these two. If we just replace time series of the selected visual metrics for its resolution, it is difficult for users to compare different resolutions and choose an appropriate resolution for reviewing intertrain information. Instead, we use the bivariate area chart to illustrate the difference between metric series for a particular resolution and the baseline. The red color means the metric values of the current resolution is higher than that of the baseline, while the blue color implies the opposite. The bivariate area charts do not modify the two metric series, so we can gain the values along with the comparison. We also implement some interaction for users to investigate vector plots of interest, including cleansing and parsing. If we mouse over the bivariate area charts, some vector plots appears for us to observe their patterns. For example, we can see vector plots at the point of interest and some plots in its neighbor. We call this interaction the lensing. If we click on one of the vector plots from placing effect, we can process and investigate the selected plot. We call the interaction the parsing. After parsing, we can interact with the corresponding vector plot to get information of its vectors and observe of its visual metrics. Moving to the use cases. There are two use cases in this representation. It is for a dataset, namely US employment data and SBCC data. We start with the introduction of the interface. We firstly introduce three main components of the main interface. The control panels located on the top left corner of the interface. We can select datasets, visual metrics, pairs of variables on its panels. The main visualization with a bivariate area chart and the baseline is on the right of the control panels. If we browse a vector plot for investigation, it will appear below the control panel along with a star chart showing all of its metric values. The first use case is with the US employment data. It has 53 states and prisons in the US and 53 data points. We select the pairs total non-farm and total rabbit, with our two economic sectors. Its time step is a month from January 2000 to May 2020. For the first use case, we select US employment dataset, translation metric, and the pairs total non-farm with total rabbit. If we look at the main visualization, there are two noticeable observations. The first one is that in most periods, the translation scores increase as resolution increases. The second one is that there is one time point when the translation score for the baseline or resolution 1 is ridiculously high. Its peak is comparable in height to the highest peak for the resolution 12. The first observation is straightforward because translation repeats the amplitude of collective trends. So if the US economy maintains its trend over a long period and most states have similar economic situations, the evolution over a higher resolution certainly has a larger amplitude or higher score. In contrast, the second observation is abnormal, and we should investigate the baseline to find any valuable information from it. If we look at the vector plot from March to April 2020, we can see that the US experienced a slight drop in the number of employees due to COVID-19. The level of crisis is comparable to the annual decrease of the Great Recession of 2008. But this drop happened much faster in only 1 month. The second use case is with the HPCC data. This data is the health readings of compute nodes from a high-performing computing center. It has 467 compute nodes and 467 data points. We need to apply binding for this data to avoid cluster issues. The pairs of variables are 2 CPU temperatures. The data were collected at every 5 minutes from 14 o'clock to 16:10 on March 21 in 2019, when the two water issues happened in the system. Moving to the second use case, we select FPCC dataset, EuroVis metric, and the pairs of 2 CPU temperatures. From the main visualization, we also notice 2 observations. The first one is that blue colors dominate most regions. Our EuroVis score of the baseline is higher than that of other resolution in the most period. The second one is that at around 16 o'clock, red regions are visible, especially for resolution 4, 5, and 6. The first observation is reasonable because temperature of compute nodes depends on many factors, so vector with resolution 1 tends to have various directions. However, if there is a collective event, such as the 2 waters issues in this case, most compute nodes have a common strength, and this strength is visible only over a long enough period due to noise of time series. The second observation guides us to the high resolution for interesting information. The system was shut down at around 16 o'clock, so all vectors point to the room temperatures. The last part of this presentation is discussion and conclusion. We start the discussion with the strength of our methods. Our interactive visualization supports the use of beta plots in time series analysis. The visualization allows comparison between different resolutions, and thus it can guide user to a resolution that they can find out interesting information. Comparison between the time series of the selected visual metrics and also the comparison between visual patterns of interest. Interactive methods that are cleansing and brushing help users to quickly investigate into vector plots corresponding to the visual pattern that they want to observe. Regarding the quickness, there are 2 main quicknesses of the method. The first one is that the visualization supports only one visual matrix at a time, and the second one is that the visualization focuses on only one variable pair, so it costs user effort in analyzing multiple pairs of variables in the data. Thank you for your attention. If you have any questions, please feel free to ask me.
Thank you very much, Bao, for this really nice presentation and a clear explanation of your technique.
Thank you.
I'm looking at the Discord channel and the YouTube channel for questions. So anyone who has some questions for Bao and colleagues, please share that with us. And while you are thinking on your question, I'll start with one. Bao. I told you the technique that you presented is dealing with a really complex problem, like interactions between multiple time series over time and how that sort of changes over time, and quantifying and visualizing that is quite a challenging problem. And we already know that temporal time series alone are already quite challenging to work with. But one question is on the transformations that you apply. One thing you do is that you find those vectors between between those 2 variables over time, and then you create those vectors, and then on top of that you create those measures and then visualize that at the end. So this is a multiple series of transformations data is going through. So what were your reflections on the interpretability and semantic nature of those of the resulting visualization? Was it easy for those of you? I don't know if you've tested it with people. Was it easy to get an understanding of what's going on? Were they intuitive? Were some of the measures more easy to relate than others? So can you comment on that complexity of the transformation a little bit, please?
Well, firstly, with our methods based on the vector plot, which we can observe both temporal and spatial information, and in the main visualization, what we use is the visual matrix that can score the visual pattern in the vector plot, and we aim to find some visual matrix that is maybe easy to understand for users. So, for example, if user want to find the entropy or want to find these outliers in vector plots, they can look at the visual matrix, so particular visual matrix for outlier or for entropy. So I think it's maybe straightforward and easy to understand for user to find any visual pattern that they want to observe.
Mm-hmm. Have you done any user testing, or was that part of this project? Not yet. Okay. Right. Just seeing if there are any other questions somewhere that I'm missing. If no, I'll ask one more. I was sort of the visualization design that you had with varying time differences. I mean, starting with a deviation of 1, deviation of 2, deviation of 3. I mean, it made me think of the spatial lag models that are commonly used in time series analysis, which are usually used to find periodicity or seasonality in the data. I was wondering whether the sort of any of your plots reveal those kinds of or sort of accommodate for the seasonality or periodicity in the data, or these patterns has no interaction with those.
At the moment, there is no relation to the periodicity of the data, but the multiple scales mean that because in vector plots, we only focus on 2 different time steps. So we need to consider multiple scale. I mean that's multiple, the different, how do you say? I define one resolution means one difference between 2 time steps of the vector plot. And you can see that each resolution shows the different view of in the level of details of the temporal change of the time series. This means that vector plots we cannot use vector plot to display the whole temporal evolution of the time series, but it just looks at only 2 different time steps. So we need multiple resolution views to show the difference between is the level detail of temporal evolution. So you can guide the user to the one that they can find interesting information.
Okay. Thank you. I mean, maybe one final question about those collection of metrics that you have in the paper. I mean, in your presentation, you talked about translation and entropy, for instance, and in the paper you have a few more. Did you, I mean, in your analysis of these metrics, did you find some being more useful than others, or some being more suitable for certain kinds of analysis tasks? Do you have some sort of notion of maybe a recipe for the users of these metrics?
Well, yeah, I think it is the contents of another paper. because our papers only apply these visual metrics to the design, and we don't discuss in detail the use of its visual metric.
Okay, okay, great. We'll look for the other paper then. Great, thank you very much, Bao, for your presentation and for your responses to the question. Thank you.
Thank you.
Hello again, everyone. Thank you very much first of all, to all the authors and all the presenters of this really interesting session, working with important and challenging problems and data examples. And I would like to thank everyone for your active contribution and questions and this discussion in this session. And also a big thanks to the technical coordination team and the volunteers for their help in this session. So this then concludes this paper session. If I'm not mistaken, this is the final paper session of EuroVA. And next up we have 45 minutes break. And then a great keynote is expecting us from Mariah Mayer. And then I think there will be some closing events. And thank you very much, and good to see all of you, and hope to see again virtually.